How can we realize more of the potential of this amazing world? Get more from every harvest and keep millions of tons of food fresh all the way to the consumer. Build the cities that let millions, like her, like them, like you, rely on a better quality of life, inside and outside. And heat homes, even through the harshest winters, with lower energy use and greater comfort. For Danfoss, to achieve more from less takes hard work, knowledge, engineering, and belief that bit by bit we can make the impossible give way, so what begins as hope becomes the reality of tomorrow. This is how Danfoss is engineering tomorrow. Mobile hydraulics engineered to deliver improved performance and efficiency, making a difference where it counts. Food production and large-scale manufacturing engineered to save energy, prevent waste, and increase quality. Infrastructure solutions that help build the cities of tomorrow and raise the standard of living for millions. Indoor climate solutions that bring intelligent heating, cooling, and control to both the coldest and warmest places on Earth. This is what drives us: to achieve more with less, to relentlessly work harder and engineer the dreams of tomorrow, today. For you, for us. Step by step, realizing the potential of this amazing world. We are Danfoss, and we are engineering tomorrow.
All right. Good morning, everybody. My name is Mohammed El-Dakruri. I'm here along with Amy to present to you about how Danfoss Power Solution uses Simio. First of all, I'd like to thank the Simio team for giving us the opportunity to share and exchange experiences. And I would start by introducing myself. My name is Mohammed El-Dakruri. I'm a manufacturing engineer. I've been with Danfoss for about 5 years now. I started as an intern, and then I got a full-time position as a manufacturing engineer in the operational services team. We do paint and packaging and shipping and receiving. That's our team. And then I'm presenting today with Amy, which she's gonna introduce herself to. Amy, do you want to introduce yourself?
Hi all, I'm Amy. I am a process engineering intern. I've worked under Mohammed for about almost a year now. I am currently a senior at Iowa State University studying mechanical engineering, hoping to get my degree finished by May of this year.
Thank you. All right, so let's start by talking about the company a little bit. At Danfoss, we have three main segments. Danfoss Power Solution, which Amy and I work for. We're number 2 market position. We have 17,000 employees and 53 factories in 19 countries. We also have Danfoss Climate Solutions and Danfoss Drives. Danfoss Climate Solution has about 10,000 employees, and Danfoss Drives have about 4,000 employees. In Danfoss Power Solution, we work in different industries like construction, forestry, and agriculture, and many more. Danfoss Climate Solution, they do work in cooling applications, district heating, and air conditioning, and also other applications. And Danfoss Drives do industries like brewery, HVAC, and automotive. We also serve different markets like marine and offshore, refrigeration, air conditioning, water and wastewater, district energy, and many more. We recently merged with Eaton, and we even expanded our footprint more. So that was a very big transition, especially for Power Solutions. And as you can see here in the map, Power Solutions had 23 manufacturing sites. Eaton had 30 manufacturing sites. Now we have 53 factories in 19 countries. All right, this is just a quick snapshot of what we do, what products we make at Power Solutions. So pretty much all hydraulic related and electrification and software. So some of the products we make in Ames, for example, are open circuit pumps. We also do other products and other power solution segments or facilities like converters, electric propelled motors, radio piston motors, sensors, and vane pumps, and other applications. So let me talk a little bit about simulation at Danfoss. We at Danfoss use simulation for different reasons. I speak about it locally in Ames, where Amy and I are located. There is a manufacturing facility in Ames, about 1,000 employees. And we do use simulation mainly to simulate assembly lines, paint and packaging and shipping and receiving applications. I know there's many other applications that Simio can be used for, like supply chain, scheduling, but in Ames, Iowa, we're just focusing on using Simio to do assembly or basically production line simulations. Globally, we have a bigger simulation team. They are mainly focused on prototyping and optimization of hardware. So basically finite element modeling and optimization of pumps and motors and other devices or other products that we make. Only recently that they started looking into production line simulation. We use Simio in Danfoss to study some layout changes or layout designs that we want to propose or develop. We do visualize transportation and material flow. We also do analysis on equipment and bottlenecks to understand how we can resolve or make production faster or increase the throughput. We also use it. We started using it recently to kind of understand how different staffing capacity or absenteeism would impact the production in our facility. So today, since it's SimiSync this time is about applications, we thought, okay, let's pick the three models from what we worked on in the past and talk about it a little bit. Gonna give you some a quick overview of how we use Simio in the plant and how did it help us to make some decisions in the past. So I'm going to start here with use case one. And for every use case, I'm going to define a problem. I'm going to tell you about the model, how we constructed the model, and then the results. So for the first use case here, it was about our receiving department. So we have a receiving department. That receiving department handles all the incoming material. So the incoming materials is being used in the assembly lines, but between the warehouse and the assembly line, there is a receiving department. And you can see here, we have to receive parts first from the warehouse, and then they get delivered to the assembly line. That being said, our warehouse, which is a bigger facility that we just store all the parts that we use to build pumps and motors, send us a truck every 4 hours. So we get a truck full of skids every 4 hours. And the way it works is that truck arrives at receiving, and then we have a forklift operator unload that truck. Now the problem becomes is if the warehouse sent us the next truck in 4 hours and the forklift operator didn't fully unload the truck, now trucks start to interfere. And if that happens, we end up with a lot of units sitting in the receiving department that hasn't been received, and then those can quickly pile up, and it's going to create a big mess. So what we wanted to understand is how can we make this process faster, and how can we avoid the impact of having one or more truck overlap. Some ideas were like, hey, we can add a second forklift operator. We can change the process, make it faster. We can do many things, but we wanted to see it and visualize it using Simio, and then get and make decisions based on that. So we collected historical truck data for a week. So we focused on 1 week worth of data from the warehouse. So basically we would know how many trucks arrive a day, what is on every truck, and where every skid or every box in that truck go in the facility. We wanted to know where storage locations are. Storage locations are basically racks And then we wanted to know forklift speeds. So we did some calculations here and get that. Loading and unloading times and possible disruption to the delivery process. So a forklift driver would be driving to deliver a box or a skid, but there could be some disruption along the way that could cause delays. And we constructed the model, and I'm going to talk about the model a little bit in the next slide. And then the outputs that we got out of this was the average time to unload a truck. So basically, if we get a truck from the warehouse, how much time it takes on average to unload it, to fully unload the truck. And then a best worst case scenarios, and then the average trip that a forklift driver make to go drop off a skid from our receiving department to one of the assembly lines. Here's a snapshot of the model. We didn't care about all the production lines and paint lines that we had in the facility. Instead, we only cared about our receiving department, which is located over here, and then all the racks in the facility that those skids are going to go into. So, and the reason we circled this, as you can see here, the difference. So if a forklift driver is picking from the receiving department and dropping off at this location, it'll be less time, right? Versus if they want to drive all the way back to this storage location here. The results we got out of this was on the top left here, you can see the trip time per storage location. So series 45 is a line, just name sort series 45, and we can think about it as a storage location or rack location. For some of them, it takes 4 minutes to drive from receiving to the racks. For some of them, it's just as little as 1.2 minutes. So that tells us, hey, how much it takes for every storage location. And then truck unloading hours. So in a best case, we would get the minimum value is 2.57 hours. So about 2.5 hours to unload a truck. There'd be some cases where we exceed the 4 hours, 4.2 hours. And there'd be, the average case is 3.29 hours. The problem with those results is there could be some disruptions that can happen that change those a little bit. And we also did it based on 1 week worth of data. If we could have had data that is like a month worth of data or a year worth of data, I think we would see the average won't change much, but you would see bigger maximum and lower minimum here. So we came up with some proposals, and one of them was, scenario 1 is just to keep it as is. That'll change. That's not going to change the average, maximum, minimum. But there's going to be another scenario when we try to reduce disruptions. Basically, make sure that every time a forklift go to drop off a skid in a rack, they have a spot for that skid. Otherwise, it's going to be a lot of wait time. Maybe take different routes, avoid congestions or times where people are walking around the factory, like break times or shift change times. So we had some discussions about how can we reduce those disruptions. And then the third scenario was if we increase the forklift speed, how would that impact the result? We didn't end up doing that because it was a safety concern. Safety team didn't allow us to do that. We also tried to reduce some of the disruptions, but the solution that we came up with here is just to come up with a new design where, if you look back here, instead of having those racks scattered along the factory, we just combine them and put them somewhere very close to the receiving department. And that helped us really achieve that 4 hours target or even less. And this just got executed, and it is doing fine, and we're still gonna continue working on it. So this is the first use case. We learned some lessons, and we had some challenges when we created the model. One of them was the truck arrival times. We had to spend a significantly large amount of time trying to dive through the data and understand what skid goes where. So that data collection was a challenge. And then it was the first time also to use data tables. At that time, we didn't have much experience with Simio. And instead of having to type everything manually, we started using data tables, and that helped us really achieve results close to reality. Another thing was simulating racks. At that time, we simulated racks as sinks, but we could have used rack objects. I know Simio have a rack object, but at that time, we just made the assumption that anything that goes to a rack is going to get distributed, which means it's going to be used eventually by assembly. And then last thing is disruption to loading and unloading. There's many disruptions that could happen. Forklift stops working, people crossing in front of forklift, a new driver that is slower than average, many things. So we had to make assumptions and pick one or two disruptions and put them in the model and assume everything else is ideal. And then I'm going to let Amy talk about the second use case.
Thank you. And then for our second case, we went into paint. We were talking about paint and packaging simulation. So this is currently the biggest simulation that we have going on in our facility. It's an active model that we continue to update, but the issue was that we had our most high volume model, which is our H1 tandem. It's a certain type of pump that is produced. We had an increase in sales, which meant that we had to have an increase in capacity for our lines. And so currently we had 8 assembly lines and we wanted to add 4 more. So we had 2 different options that we were looking at for which one would be the best. And then we put it through the simulation with all of our different units and so wanted to see how much would be, wanted to see how much time it would take to go through the model. We collected some of the different inputs we had for this model was the cycle times that it takes all the different units to go through the line, the product arrival rates that came at paint. We use data tables for those, which I'll get into a little bit more later. Um, for the different paint robots, they all have different colors that they do for the different units. So we had to put that into the simulation model. Downtime data, so when it wasn't being used, when the downtime, and then we had the automated vehicles. We use automated vehicles to get from one side of the paint line to the other. So we put in how much time it took for that to happen, and then some of the staffing schedule because we do run on a 3-shift staffing schedule. So seeing which had units and didn't. Then I'll go into a little bit about the model in a minute, and then just some of the outputs that we wanted was we wanted to know the total time in system for each product and then the wait time in packaging because sometimes they could be waiting on the pack lanes for about 30-ish minutes and we wanted to see how long it took for them to be sitting in packaging before they actually got packed. So this is just a little bit more about the model. This is a video. As you can see, we go from assembly all the way, it goes from our assembly lines all the way through paint. We have 15 assembly lines with different products that we make in colors. There are some automated stations such as our paint booths and they don't have any operators in there. It's just from the paint robots. And then we also have stations with our operators that have all the different shifts on them. So how much time it takes for them to do each certain unit, because sometimes it takes longer to do a unit than another. And as you can see right now, those are the pack lanes that we use. And then we got results using this with all the different times that it came in. We ended up choosing option 2. It allows, as you can see with option 1, there was a lot more congestion that could happen in the lines where our units could get stuck. So units would go down the lane. Those are the triangle entities. And then once they get packed, a pallet comes back out and has to get recirculated throughout the line. But if there is a holdup, or as you can see where the green units are, there were all the pack lanes were being used. So everything had to be held up. So we ended up going with option 2 to stop the holdup with all the other lines. And now it's only, so since it's an extra long assembly line, it only stops from 3 other lanes instead of the other 8 lanes that we have. And we ended up executing this over a year ago and it's been working really well. Uh, just some of the challenges and the lessons that we learned. We got product arrival rates. We started using data tables. We learned how to import data from Excel that we got from our actual lines out on the site floor. And we got to see how many units went through the line at once. And we were able to put those in Simio and import them so we could make sure that it was as accurate as possible. And then we went through a little bit of the process logic. We had over 100 different add-on processes. So something such as the paint robots had to be coded to see which one it could see which unit it had and then decide what color to put onto it. The biggest problem we've had so far is that the model is becoming very large, putting all the different units and all the different processes in there. So it becomes harder to maintain because you change one thing and it can change the entire model. And then one other big thing that we need to work on is having more documentation. So if any other engineers looked at this, they could see what we were trying to do with this model and see what each place means.
Right. Thanks, Amy. Um, and yeah, just like Amy said, when we started this model, we didn't know that it's going to become one of the biggest model that we ever worked on. And if we can go back and kind of document that and make it look a little bit tidier, that's one advice that I would give to everybody who's just starting a simulation model. Is, make it easy to maintain and fix and have very good documentation. All right, so the last use case that we have is the easiest out of the three, and it was also different. This time we were not interested in understanding how the production or the throughput of a production line would be impacted. Instead, it was mainly a safety concern. So we had a project that involved buying a new pallet wrapper, as you can see here in the picture, and that new pallet wrapper needs a new home. So we identified a spot in the factory that we want to put the new pallet wrapper at. There was a concern that when that pallet wrapper is placed into the new spot, that's going to increase the forklift traffic around that area. And that area is also congested with people, especially at shift changes. So our safety team asked us if we can simulate how many times or how many interactions are going to happen between people and forklifts loading and unloading to the new pallet wrapper. So we put a camera at that new location of the intersection and counted how many people would cross that intersection at a given time. We also get cycle times about the speed of automated vehicles, forklifts, and when and how many of those are going to cross that intersection at a given shift. We had load and unload times from and to the wrapper also as inputs. And then we constructed a model. It was a fairly simple model, just the automated vehicles, the forklifts, people walking around, and then the pallet wrapper. And we ignored everything else going around that area. And then the outputs we were looking on is percentage increase in traffic congestion at the new wrapper location. And we needed to come up with something that tells us if or how much congestion are we adding if we add that new wrapper in the new place. So that's a snapshot of the model. You can see here, this is a pedestrian trying to cross that intersection, but there's also a forklift. And in that case, our forklift operators will wait for a pedestrian to cross. That creates larger cycle times for forklifts. And it is also a concern of, if there's too many people crossing and there's too many forklifts crossing, our safety team gets concerned there. So if you look at the two pictures I have here, this is how we try to quantify the traffic congestion, because it's not just how many people crossing that intersection, right? It is how many people trying to cross the intersection when a forklift is loading or unloading to the wrapper. So we identified some red zones here. So here's a red zone, and this is all pedestrian aisles. Here's a pedestrian aisle and a crosswalk. And here's an example of somebody walking by the forklift while the forklift is unloading his kit from the pallet wrapper. So every time somebody is walking into the red zone and a forklift is present here, we're going to mark this as one incident. And then we started counting how many incidents. Of course, it's not a safety incident. It's not like an accident or anything. We just call it an incident that somebody is walking by the forklift while it is operating. It happens all the time in the facility, but in this case, the forklift needs to back up all the way, right? Sometimes they need to back up to the pedestrian aisle and then move forward. So that's a safety concern. So here's the results that we got. Scenario one is a current state when we don't have a wrapper, right? If we don't have a wrapper, there's 26 incidents where a forklift is going to wait for an operator to cross, and there's 0 incidents that a forklift that is loading or unloading to the pallet wrapper would wait for a pedestrian. Scenario two is a future state, and that future state, in that future state, we're increasing the number of times that people are trying to cross that intersection is going to be 34 instead of 26. And then there's going to be 45 times where somebody is walking by the pallet wrapper where a forklift is loading and unloading. And at the end, the results that we got out of this, okay, there's going to be an average 45 times that a person is going to be walking by the forklift while it is operating, and we're going to increase the congestion from 26 to 34, which is about 30%. And that was okay. Our safety team was okay with the results, and we moved forward with purchasing the wrapper. It has not been installed yet, but it should be happening here soon. We didn't have much challenges with this because it was fairly simple model. The two big challenges we had, or lessons learned here, is we needed to come up with descriptive variables to describe the results, right? At the end, somebody's going to ask you to make a model, but you want to say, hey, we want to know if it is safe or not to put a wrapper here, but they don't tell you what exactly you want to measure, right? So we need to just think about what variables can we come up with to make that measurable. And then the other thing is there's a lot of moving objects. So we have forklifts, we have pedestrians with carts, we have automated vehicles. All of them can cross at the same time. And we needed to put some logic here to know which one is going to wait for which, right? So usually everything waits for pedestrians, right? But then what happens when we have an automated vehicle and a forklift? Who waits for what, right? So we had to define that logic and put it in the model. So we covered all three cases. To wrap up here, I just want to give a thought on what we think about the future of simulation at Danfoss. Internally in Ames, Iowa, we're at work. We are trying to grow the number of people learning Simio and knowing how to construct simple models. We're also taking the initiative to implement simulation whenever relevant. So whenever we have a project that and time permits and we can use Simio to really benefit us making a decision, we would do that. And we also educating our peers and, hey, this is Simio, what it does, how can we use it for future projects, and so on. And globally, we haven't yet collaborated with a global team on simulation, but we are planning on doing so. I also know that they are expanding their team and they're adding people specializing in production line simulation. With that, I think that's everything that we have here. Please let us know if you have any questions. Thank you.
Thanks, Mohammed, for such a thorough presentation. It was really great to see the diverse use cases there. We have really only time for just like one question here. So there was a question around the first use case, and if you were you all able to determine the impact of moving to more of a centralized storage location on the other operations within the plant, or was that still out of scope of the project at this time?
We didn't do it yet, but we're planning on redoing the simulation again when we fully execute that project. But we can tell we had a trip time for every location in the factory, and you can tell that all those trip times are going to reduce at least in half when we get everything closer to the receiving department.
Okay, great. All right, well, like I said, I know we're short on time here, but it was a great presentation. We really appreciate you being a part of SimioC. So thank you.
Thank you for giving us the opportunity to present. Thanks.
This concludes this presentation. Please click on the back button to access the next presentation.